Hello, Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering, and this is the video where I discuss the solutions for the third exam in the winter 2019 semester. And so the first question I want to discuss is question 1, the short answer question, and I'll just talk about the solutions. So for problem 1a, in a non-inverting op-amp amplifier where we have the output voltage being equal to A times the difference of the input terminal voltages, and R1 and R2 are the resistors in the amplifier design, why do we refer to A times R1 divided by R1 plus R2 as the loop gain? And so basically, even though I don't give you the schematic, what I wanted you to do for this question is to remember the layout for the non-inverting op-amp amplifier, which is the one we discussed in the lecture videos, and to know that the feedback path from the output to the negative input terminal is through the voltage divider R1 and R2. And so basically the feedback loop gain is just the voltage divider equation, R1 divided by R1 plus R2, and then the forward part of the gain is equal to A. And so the product of the voltage divider equation and the the forward gain A is what we call the loop gain, because it goes all the way around the forward path and the feedback path of the loop. For part B, what's the difference between dB and dBm? dB is basically 10 times the base 10 log of a power ratio, P1 over P2, and dBm is 10 times the log base 10 of a power divided by 1 milliwatt. For part C, how do poles and zeros behave differently as frequency, as the angular frequency omega approaches infinity? So it doesn't matter if we're talking about a simple pole or a pole at the origin, or a simple zero or a zero at the origin. As omega goes to infinity, all zeros all zeros have a response that goes to infinity, and as omega goes to infinity, all poles have a response that approaches zero. And finally, why do we call B the negative short circuit transfer impedance? Well, this of course refers to B in the ABCD transmission parameters. And what I was looking for here is basically, what most people did is they just wrote down the formula for it, and they said it's equal to V over I, which is basically the formula for impedance, essentially Ohm's law. And there's a negative sign in front, so that's why we call it negative. But I was looking for people to say that V over I is equal to impedance, or it's the definition of impedance. Question 2. Question 2 basically is asking you to consider the design of an RC low-pass filter and an RL low-pass filter, but with the parasitic capacitances included. And the first thing to recognize is that the parasitic capacitance for a capacitor is in parallel to the capacitor, and the parasitic, or the winding resistance, for the inductor is in series with the inductor. And so for part A, in an RC low-pass filter, would the parasitic resistance in the capacitor increase or decrease the corner frequency and increase or decrease the passband gain? And so for the passband in a low-pass filter, the passband gain in a low-pass filter, that's basically the value of H omega for omega equal to 0 is the easiest way to calculate that one. So that's kind of similar to what we did on the assignments. So a low-pass filter is designed to pass low frequencies, and so you can use omega equal to 0 basically for that, determining that passband gain. And I'll illustrate that in a moment. So this first part is the capacitor case. And so we have the parasitic capacitance in series with the ideal capacitor. And what I've done in my solution is I just find the equivalent impedance of the capacitor in parallel with the resistor, and the equivalent impedance, we can just use the parallel impedance formula, so the product of RP and 1 over j omega c. Then once we have Z or the equivalent impedance, then we just use the voltage divider equation to determine the output voltage as a function of the input voltage. Then we take the transfer function as the ratio of the output and input voltage, and then if we sort of simplify things a little bit, we can put the equation in the standard Bode plot form, basically. So if we're asking about the corner frequency, what we need to do is we need to separate all sort of real valued gain terms out front. So this would be the K parameter in the Bode plot equation. And then we have one simple pole in the right-hand side of this equation, and we want to lump, all of our terms so that we have j omega times some factor plus 1, and that's the standard form. And if we do that, we can compare this. We know that we've got C times RF times RP over RF plus RP. And so this is the, I guess it would be the 1 over alpha term. And if we compare that to the 1 over alpha term for a standard filter without the parasitic resistance, if we just had this standard low-pass filter without RP, 1 over alpha would be C times the filter resistance. But we've got C times the filter resistance in parallel with the parasitic resistance. Now, when you put two resistances in parallel, right, and this is the formula for two resistances in parallel, the result is always smaller than the individual resistance values, and so this equation is always going to be, or this term is always going to be smaller than this term, and as a result, the cutoff frequency is going to increase. Now, if we want to look at the passband gain, that's just this term here. And so again, if we compare this to a standard RC low-pass filter with just a resistor in parallel with the, just with this filter resistor in series with this capacitor, the passband gain of the filter is actually equal to 1. However, with the parasitic resistance, we have this term out front. And because RP over RF plus RP is always going to be less than 1, then the passband response, or the passband gain, decreases relative to an ideal filter where RP is not present. And we can do something similar for the winding resistance in the inductor. The algebra is actually a little bit easier here because we don't have parallel terms. We've got our, I call this RP still, but this is the winding resistance. So this is the winding resistance in series with our ideal inductor. And our output voltage, just using the voltage divider equation, is RF over the sum of all of these series impedances. And this is the transfer function equation put into the standard Bode plot form. And similar to how we did for the RC equation, we want to, this is our 1 over alpha factor. And if we compare it to the 1 over alpha factor for a standard RL low-pass filter where the winding resistance isn't present, we can see that L over RP plus RF is less than the standard 1 over alpha value, which is L over RF. And so because this term is smaller, the presence of the parasitic resistance increases the cutoff frequency. And again, because the gain of our low-pass filter without this winding resistance is equal to 1, because we now have this term out front with the winding when the winding resistance is present, and because this term is always less than 1, then the passband gain will decrease as a result of having this winding resistance in series. And so how I marked this question, basically I kind of assigned, roughly speaking, 2 marks for each part of the question. You know, the passband or the corner frequency for both filters were each worth 2 marks. The gain for each filter was each worth 2 marks. Some people didn't put the parasitic and winding resistances in the right format. Some people put the winding resistance in parallel. A few people put the parasitic capacitance for the capacitor in series. I took a mark and a half off for that, and then that was probably, I would say, the most sort of common equation. And then if other people made mistakes, it was kind of maybe getting there were a few errors perhaps in deriving the transfer functions. Okay, question 3 had 3 parts, and the way I sort of distributed the marks is A and B were each worth 2 marks, and then the Bode plot part C was worth 4 marks, roughly. And in the question, I give you the response of a low-pass filter and a high-pass filter, and what you should recognize about these responses is that the low-pass and high-pass filter responses I give you in the question are the standard ones that are derived assuming that nothing is connected to the output of the circuit. And so for part A, if you directly connect the filters together, the overall response of the cascaded filters is not the direct product of the low-pass and high-pass filter responses that I give you. And the reason for that is because these transfer functions assume that nothing is connected to the output. As soon as there's current flowing out of the low-pass filter into the high-pass filter circuit, the response of the circuit changes. And we've done a fair bit of this in the class, in particular working through the assignments and looking at what happens when we add a load resistor to a low-pass filter, for example. And so that's what I was looking for part A. Some people answered this part A in terms of the ABCD parameters. They said that the proper way to determine the response of a cascaded system is to use ABCD parameters, and they sort of went that direction with their answer, which was totally fine. I gave full marks for that as well. If you, for part B, if you incorporate op-amps into your circuit, 1 or more op-amps, is it possible to cascade the low-pass filter and high-pass filter and have a response that is equal to the product of these two transfer functions? And the answer is yes, if you use buffers. So this is a drawing of the circuit. For sure you have to have one in between the 2 stages. You actually do have to have one at the output. Most people didn't have that, and that was okay. Like I still gave full marks if you just had one in between the 2 stages, but just be aware that you actually would have to have one at the output as well, if you wanted to hook something up here. And so the reason why this works is because, first of all, when you connect the output of the op-amp directly to the negative terminal, you get a non-inverting amplifier with a gain of 1. And when we connect the output of the low-pass filter into the op-amp terminal, because the input to the op-amp has got such a high resistance, essentially no current will flow here, and all the current will flow down through this loop through the capacitor to ground, and that's what our original derivation of our transfer function assumed. And so this is a way to make it work. This is also kind of a handy, I guess, sort of quick and dirty way to design cascaded filters together if you've got some op-amps and you're not doing a particularly high frequency design. Some people did put an op-amp at the start of the circuit. What that would do is it would amplify the input, but it still wouldn't allow you to cascade, or it still wouldn't allow you to multiply the transfer functions of the low-pass filter and the high-pass filter together, because as soon as you connect this point directly to that point, you've got circuit flow, or you've got current flowing through this branch and that changes your transfer function. So you need to put something in between these 2 stages that will prevent the flow of current from one stage to the next. A few other people sort of incorporated capacitors and resistors into their feedback path. That is a design technique for sure. I mean, you can make active, what they call active, low-pass and high-pass filters by incorporating capacitors and resistors into the feedback path. You know, most of the answers I saw, I wasn't able to sort of see that design carried through to understand sort of the overall transfer function. But if you do have something like that on your paper and you know you do feel as though you proved that the transfer function is equivalent, then I'm certainly willing to look at it. But I did take a close look at all of the solutions that were like that, and I couldn't quite follow many of them through. And then finally for part C, this is a Bode plot question. So here we have the product of our two transfer functions. Getting this into standard Bode plot form, we pull the gain factor out front. This is our factor K. We have a 0 at the origin, and then we have two simple poles. And then basically this is the rest of the solution. So plugging in our component values, R1 times C1 is equal to 0.01. R2 times C2 is equal to 0.2. The value of K, which is just the product of R2 and C2, is equal to minus 14 dB. This should be dB. And our corner frequencies are omega equal to 100 and omega equal to 5. And so if I plot, our simple, our 0 at the origin, it looks like this, positive slope of 20 dB per decade. Our first simple pole has a gain of 0 and then a minus 20 dB per decade slope starting at 5. The second one has the slope starting at minus 20. And when you add all of these together, you have, because of this minus 14 dB gain, you have at an omega of 1, we have our response starting at minus 14. If we want to see how much we rise between an omega equal to 1 and omega equal to 5, we can calculate our value of K1 as being equal to minus 14, which is where we're starting, plus 20, because that's the slope of our line, log of the ratio of the end frequency and the start frequency, 5 over 1. And if you do that, you get approximately 0. It's not exactly 0, but you can draw it as 0. And so that basically means we rise up to 0. We go across at 0, and then at starting at 100, we go down at a slope of minus 20 dB per decade. And again, to get full marks for your plots, I wanted everybody to sort of have this shape, obviously, and I wanted to know the values of the Bode plots at the points where the response changes direction, and also I was looking for the slopes of the line as well. Looking for was a cascaded ABCD parameter question, and generally speaking, this one was quite well done. This might have had the highest average of all the questions. So we have our first system, which is a sort of a standard RC high-pass filter, and then our second system, which is a standard RL low-pass filter. And basically you had to determine the ABCD parameters for these two systems and then multiply the T matrices together to determine the A parameter to get of the overall cascaded system to determine the voltage transfer function. And so here's here's the first part of my solution. So this is the voltage transfer function for the RC high-pass filter. I'm just giving it to you because we've derived it in either in class or on the assignment, so you have the solution for this. I wasn't sure, I think maybe we did this one too, but anyways, I re-derived it. So the A parameter for system 2 is V1 over V2 when we have an open circuit, and that's just equal to the inverse of the voltage divider equation. So this is the A parameter. The B parameter is the negative of the input voltage divided by the current going in the upper branch when we short circuit the output. That of course short circuits R2, and then we just have really V1 applied across our inductor, and so the current is equal to V1 divided by the impedance of the inductor. The negative signs cancel and we get j omega L. C is the input current divided by the output voltage when we have an open circuit. When we have an open circuit, the current flowing through this loop is equal to the current flowing through the resistor R2. V2 is the voltage across the resistor. So we have V2 divided by R2 giving us the current, and then of course we leave V2 on the bottom to cancel, and then we get 1 over R2. And finally for D, it's the current ratios, input-output current ratio when we short the output. When we short the output, all the current flowing through I2 is going to, all the current going into the circuit is going to flow through the short, and so these two currents are equal, although in negative or in opposite direction, and so the opposite direction part gets rid of the negative sign, and D is equal to 1. And so the transfer function equation for system 2 is just given by this, and then the overall transfer function matrix, ABCD matrix for the cascaded system is just the product of T1 and T2. And because I'm just asking you for the voltage transfer function, we really just need the A parameter. And so I just take the first column, multiply by the first row, and that's what we have here. I did a little bit of simplification here. I didn't ask you to do it. If you left your answer just in terms of this and then said H omega is equal to 1 over A, I accepted that. But I did maybe one more step here and flipped it over. And then that's the solution that I was looking for. Okay, this last question. This last question was kind of a system level question. It was I thought one of the trickier questions on the exam for sure, because it really does sort of piece a lot of concepts together. And so basically we've got a transmit voltage, or I'm calling it in my solution a transmit voltage, that goes through a coaxial cable to to turn into a received voltage. The received voltage then passes through an RC high-pass filter to give us a voltage level VF, and then we have some linear gain value, voltage gain G. And the question says, if we've got 5 volts for Tx and we want 3 volts for at the output of our circuit, what does G have to be? And so the way I divided my solution is to sort of go kind of step by step, right? So the way I tackled it was to say, okay, well, let's do this first stage where we've got 5 volts here. What's our value here? And the gain of our coaxial cable, or I use A here because it's to represent attenuation, is equal to 10 to the minus 5 divided by 20. This has to be 20 because we're dealing with a voltage gain. So our linear gain is 0.562, and then our voltage at this point in the circuit is equal to 5 times 0.562, or 2.81. Now, the transfer function of our high-pass filter is just given by this standard form, and the cutoff frequency is equal to, oops, sorry, and this should be an omega, not an F. omega c is equal to 1 over RC, which is 2 times 10 to the 4. Now, in the question I say that we're oscillating at 200 hertz, and so our omega value is equal to 2 pi times 200. And this, of course, is less than the corner frequency for the high-pass filter. A few people said, okay, well, it's less than the cutoff frequency, so we can assume that it's 0. And you can't actually do that. So these filters, rather than having a sort of a brick wall response that looks like this, they really do, and we've seen this on the assignments and on, when we do our SPICE simulations, they have a response that looks like this. And so even though, omega c might be right there, we're down here and there still is a gain, it does attenuate the signal, but it certainly doesn't make it 0. And so the way to determine the gain of this, this RC high-pass filter, you can sort of try and power through the complex number math. A few people did that. A few people did that successfully. But the easiest way to do it is to just use the Bode plot equations and evaluate the Bode plot to recognize that this has a simple zero, or sorry, a zero at the origin, a simple pole, and a k factor equal to r times c. And then to plug in our RC values, but also just plug in our particular value of omega. So rather than plotting this, creating this as a plot versus omega, we have a particular value for omega. Omega is equal to 2 pi times 200. And so you can plug that specific value in there and get an attenuation value of minus 24.05. And so the linear gain of our, this should be high-pass filter, not low-pass filter, is equal to 24.05 divided by 20, 10 to the power, so 6.27 times 10 to the minus 2. And so the voltage at the output of the filter is equal to the voltage here, 2.81, multiplied by this gain factor of the high-pass filter. So we get 0.1763, and then we want our output to be equal to 3 volts, and so the gain factor of this last stage is 3 divided by 0.1763, or in other words 17 in linear terms.